Hi, this lesson is going to be presenting a number of tests, showing tests for convergence with respect to series. And so I will leave it to you to pause and just read through these tests if you haven't done so already. You have the integral test, comparison test, limit comparison test, alternating series test, and then the ratio and root tests. And we are going to demonstrate all of those within this and the next video. So let's go ahead and start practicing applying some of these tests. And in the first problem, we want to determine if the sum of the natural log of n over n converges by the integral test. Now, the integral test requires a few things. The function f has to be continuous and positive on some interval n large n and above, and it needs to be decreasing. Remember that f of x comes from your an sequence. You just replace the n with x, and so our f of x here is the natural log of x divided by x, and it is continuous for 1 and larger. Now, it is actually continuous above 0, not including 0, but usually, since x corresponds to n and n is a counter, usually starting at 1, typically the interval you're looking for is where you're starting at 1 or a larger integer. But in this case, 1 works out fine. So it is continuous, and x, being that n is going to be 1 or greater, x will be positive and the natural log function will be positive, and so we have it's continuous on this interval and positive. So that's the first criteria that needs to be satisfied. The next is we want to know, is f decreasing? So one way to do that might be through the first derivative test from Calc 1. And when you take the derivative, you've got low d high minus high d low, the derivative of the bottom, over low squared, which simplifies to 1 minus the natural log of x over x squared. And you'll notice that it's decreasing when this is negative. That's what we want to know. Now, we know that the denominator is never going to be negative because x squared, whenever you square something, that is going to be non-negative, so 0 or positive. And so the only way this is going to be negative is if the top is negative. So we want to know when is 1 minus the natural log of x less than 0, and that will be when the natural log of x is greater than 1. And taking the exponential of both sides, that is going to be when x is greater than e. Now, e is approximately 2.7 and change. And remember, x is actually a counter. And so this is really going to be or correspond to n greater than or equal to 3. Now, keep that one in mind. We're going to make use of it at some point. It doesn't have to be right now. Working with e is going to be fine. But we satisfy continuity, positivity, and decreasing. And so the integral test says we want to look at the integral from e to infinity of the natural log of x over x dx. And so looking at this integral, I see that u substitution would be a great method to use, where u is the natural log of x, and du is going to be 1 over x dx, which gives us the integral of u du. So u is the natural log of x, and then the 1 over x dx remaining is du, And when we integrate this, we have u squared over 2, which is the natural log of x, this quantity squared over 2. And we're evaluating that from e to infinity. And what we have is that the natural log is going to be natural log of infinity. That's going to end up being infinity minus the natural log of e, which is going to be 1 or 1/2. But no matter what you subtract, this is still just infinity. And so since the integral is divergent, this implies that the series also diverges. And so that's how you would apply the integral test. It is important to check that the criteria are satisfied, numbers 1 and 2. Now let's go and figure out how to apply the comparison test. Again, we already know the answer now. We just need to figure out how to get it using the comparison test. So the comparison test notes that in part A, just to save some work, we saw that the natural log of n must be greater than 1. And so I just replaced x with n here. So I'm looking right at this step in the middle. And we know that has to hold for n. So natural log of n must be greater than 1. And if you divide by n, that means that the natural log of n over n must be greater than 1 over n. Now note that this gives us a bound, and we had even found in part A that this will hold for sure for n greater than or equal to 3. So this gives us a bound. In the last handout, we proved that the sum of 1 over n, which is a harmonic series, diverges. It wasn't an especially pretty proof, but it does work. And so it is important to actually explore that, but it does diverge. And so that diverged for n from 1 to infinity, but even if you take out when n is 1 and 2 and start from 3, it still diverges. So those two terms aren't going to change the fact that it ends up getting larger and larger and thus diverging. Now, since the sum of 1 over n diverges, and the sum of the natural log of n over n is going to be greater than the sum of 1 over n, we know that the sum of the natural log of n over n also diverges. And so essentially, the harmonic series is going upward, and since that's a lower bound for the series that we're actually interested in, it must also be pushing the sum of the natural log of n over n upwards too. That's why since the harmonic series diverges, so is the series that we're actually interested in. And so graphically, it's interesting to consider the behavior. So that's problem 1. You got a taste for the integral and the comparison test. Problem 2 is letting us use the ratio test to demonstrate what we might learn. And so here we want to test the convergence of the series n to the nth power over n factorial, and we want to use the ratio test here. And so we have that an is n to the nth power over n factorial, and this means that n plus 1 is going to be n plus 1 to the n plus first power over n plus 1 factorial. And what we're going to be interested in our limit is an plus 1 divided by an. So now that we have those two terms, we could write them out. We've got n plus 1 to the n plus 1 power over n plus 1 factorial divided by n to the n over n factorial. This is going to be the same thing multiplied by the reciprocal of the bottom. And here we could start simplifying a little bit, and so I could see that n plus 1 to the n plus 1 term over n to the n, I'm going to bring those two together, but then I've got n factorial over n plus 1 times n factorial. So that is n plus 1 factorial essentially on the bottom, but rewriting it this way lets me cancel out the n factorials. And I could even manipulate the, let's see, n plus 1 to n plus 1 on top, divided by the n plus 1 on the bottom, is going to give me n plus 1 to the n over n to the n, which is n plus 1 over n to the nth power, or 1 plus 1 over n to the nth power. And so now we are ready to look at our limit. So we want the limit as n goes to infinity of an plus 1 over an. And in particular, what we're actually interested in with the ratio test is the limit of the absolute value, which is the limit, now we're ready to plug in, of 1 plus 1 over n to the nth power. And this is a well-known limit that you may have seen back in Calc 1, but this happens to be e. And since e is greater than 1, this tells us that the series, the sum of n to the nth power over n factorial, is divergent. So that's what we learn in this case from the ratio test. Again, what we're looking for, in case you didn't quite read the initial summary pages, the ratio test looks at what the limit of the absolute value of the ratio is. If it's equal to 1, then you don't learn anything. If it's less than 1, so if it's really small, you learn that it absolutely converges. And if it's greater than 1 or infinity, then we know it diverges. And in our case, our limit was e, which is a value larger than 1. And so that's why we know that the series diverges. Okay. So that's what we learned from problem 2. And the remaining problems I will continue in the next video.